So, hi and welcome everybody to the lecture titled Angle Modulation, which is a part of a series of lectures related to Introduction to Communication Systems. In the previous lectures, we talked about amplitude modulation, double sideband suppressed carrier, single sideband, vestigial sideband. We studied the transmitter design, the receiver design, the mathematical modeling at the transmitter, and how to detect and demodulate the signal at the receiver side. And we explained the advantages and disadvantages of each one of these schemes. And we said what might be applicable for certain application, it cannot be possible to be applied for certain other applications. So based on the requirements of the application and the needs of the user, you determine which modulation scheme you are going to use. And this is basically what we have been studying up until now for introduction to analog communication, basically. Now we are moving, so basically if we want to classify modulation and write the word here modulation, we classified it up until now into two types, you can say. Yes, we have amplitude modulation, and we studied four types of amplitude modulation, and we have angle modulation. So in this lecture, we are going to investigate and study and learn angle modulation. So everybody remembers with me that modulation is all about changing the properties of the sinusoidal signal, which can be cosine omega ct. Yes, this is the general sinusoidal signal equation. Everybody agrees with me? A cosine omega ct. Now, plus theta in general, if you wanted to make it general. So what we were doing here, up until now in the course, we were changing somehow the amplitude, playing with the amplitude of the subcarrier according to the message signal, M of t. Based on the message signal characteristic, we were varying the amplitude of the carrier, A. Now, from now on, we will be discussing angle modulation. In angle modulation, forget about the amplitude is constant. We will be playing with this part. We'll be changing the frequency and the phase according to the M of message signal. And now one might ask, why do we need to change the frequency and phase according to the message signal instead of amplitude? I tell you simply because when you change the amplitude, you make your signal fluctuate as time passes, and this fluctuation can increase beyond the capabilities of the power amplifier that you have at the transmitter. And this might hurt the transmission process and increases peak to average power ratio, and then creates intermodulation product that can cause interference and limit the coverage of your modulation scheme. So to avoid these problems, we sometimes prefer to have constant amplitude, constant envelope, where it's going to be super easy to deal with using the power amplifier, and we just embed our information into the frequency or phase of the carrier, which is very nice thing. Give me example on this. FM, for example, the radio you listen to in your car or at home sometimes is using frequency modulation. So the angle modulation can be frequency modulation, which is this part, FWC, or phase modulation, which is this part, theta. So these are the topics we are going to explain in these lectures. Go over them, understand the transmitter block diagram and how the receiver detects this, and the mathematical modeling for frequency modulation and phase modulation and the relationship between them. Can you move from frequency modulation to phase modulation or phase modulation to frequency modulation? And then study the bandwidth of frequency modulation for the case of narrowband transmission and wideband transmission, where your bandwidth is really large. So these are the things we are going to be explaining. So let's get started then with the exact definition of frequency modulation and phase modulation, and how are we going to achieve that. So before that, let's give you an example about some of the tools that we use in order to see the spectrum. In our case, in the spectrum, in the frequency spectrum that we usually deal with. So in this case, for example, we have usually some devices. I couldn't show you the picture, maybe there is a problem in showing it, but in general we have some devices, we call them spectrum analyzer. These spectrum analyzer, we use them in order to capture the signal in the air and represent it in the frequency domain and show it in time domain and see the relationship between them. So we have what we call it, like you have in the window of that device that you can open it from a computer or a PC. You have your frequency here, and you have also the power of your signal, power spectral density, the density of your signal at certain frequencies. So basically sometimes you get signals like this. So we call this the power spectral density of your signal. You see your signal in the frequency domain. If you want to find the power, of course, you calculate basically the area under this curve, power spectral density, if this is power. And if it is time, this device also shows you the signal in time. You basically square this and integrate over the time to find the total energy of the signal. Now, what's interesting that you can also see the behavior of your signal in time and the frequency simultaneously. So basically the device gives you one axis here, let's say time, and here frequency, and here shows the density of your signal. There will be here a kind of a bar that starts from, let's say, white until white, red, green, blue, black, until, let's say, red, extreme red. So, and this area is composed of these colors, white, red, blue, black, whatever. So when the area becomes closer to the red, when the color of the area becomes closer to the red, means that the signal energy or signal power is extremely high at this point. So it shows you where is your signal is located right now. And it's very useful to understand the behavior of your signal and at which frequency and at which time your signal is appearing, or your signal has energy and power, so that you can detect it, you can understand the behavior of it, you can modulate it, you can filter it. So we call this process or this diagram spectrogram. So spectrogram shows the spectrum of frequencies as time varies, and the spectrum with the density of the signal means how much power it has at certain point in time and the frequency. Basically as if you are defining the location of certain thing, but location in time and the frequency. To determine location, we usually need to determine the x-axis, y-axis, and the z-axis. How the altitude, the longitude and the altitude. But for signals, we don't have something x and y, and we have something we have time, frequency, and density of the signal. So this is very useful, and if we go to the communication lab, you can also see use USRB devices or software-defined radio to see the frequency spectrum of your signal, which is super easy with LabVIEW and USRB. You don't need to have very expensive devices to check these things. So basically, this is just brief overview about these devices that we can use to analyze the signals that we transmit. We analyze them at the transmitter. We check them, see how are they before we transmit them, and how are they after we receive them, and after we process them. It enables us to debug the system and understand the characteristics of the signal. So having explained this, we go to the frequency modulation, or the mathematical modeling of the frequency modulation in general. Yes. So in principle, frequency of a signal at an instant in time depends on entire signal. This is based on Hilbert transform. We know it. That if you want to find the frequency of a signal at a certain point of time, you need to take into account the entire signal, because it depends on the duration of your signal and how frequent your signal changes itself or repeats itself. For generalized sinusoids, we can use a simpler approach. Yes, let's call this phi of t and this theta of t, and phi of t in general is given as a cosine theta of t. A is the amplitude. Anything related to amplitude modulation plays with this. Anything related to frequency and phase modulation, or in general angle modulation, when you say angle, it's basically frequency. It involves frequency and phase. So now we will see how can we determine which one of these we are using. Then theta of t is the generalized angle, this theta of t. For a true sinusoid, theta of t, how do you write theta of t in general? It's omega ct plus theta 0. Think of this. If I ask you which type of equation is this, it's linear, obvious, because you have one variable t of degree 1 and the function is changing with respect to it. So if this is linear, kind of a line, so WC acts as the slope of that line, and theta 0 as the shift. Yes? So basically, let's look at this figure to get a better understanding. So here we draw this figure. Suppose that this is theta of t. Yes, this is the signal, theta of t. Yes. And I told you, find the frequency, the instantaneous frequency at this point. What do? You make a slope, or you derive it at that point. You make a slope like this line. Yes. And here time, and here theta of t. So the slope here is WC, the slope of this line. How do you find it? Delta, the difference in y-axis over the difference in x-axis. What's the difference in y-axis? Theta, difference in theta, over the difference in x-axis, difference in time. This is omega c. Now the point, the crossing point here, we call it the offset, which corresponds to theta 0. So basically, this is what I'm talking about. So the instantaneous frequency in general, if I give you theta, and tell you find the frequency, what do? We already know from physics that the frequency is the derivative of theta. Yes, derive theta with respect to time, you get frequency. Do you remember this? If you don't remember this, let me ask you, how do you find speed? Speed of a subject from physics. Speed is equal to distance d over time. Yes? This is linear. This movement, this equation, the speed, is related to linear movement, linear actions. Now, suppose your movement is kind of circular or periodic or something like repeats itself with a frequency. It's not just going in one direction from this. What do we measure here? We measure rotation related to theta, yes? And theta within certain time, we call it what? We don't call it speed, we call it frequency, f. And here, if you want to find the instantaneous thing, which is the derivative, basically, you derive theta with respect to time. So this is from where omega comes in. This is the relationship between theta phase and the instantaneous frequency. If I ask you, give me theta, you have the instantaneous frequency. What do? Theta is the integration, yes? You integrate both parts. The integration of delta theta is theta of t, and you integrate here omega I u delta u, and from minus infinity to t. And the integration from minus infinity to 0 gives you theta 0, which is the phase offset, and then you put the remaining integration separately on the other side. We can now modulate a generalized sinusoid by using a signal m of t to vary either theta of t or omega I of t. Yes, the general sinusoid that I explained to you, we can use it to vary theta of t or omega I of t. In either case, the frequency of the modulated signal changes as a function of m of t. It says whether you vary time, whether you vary the frequency, the instantaneous frequency, or you vary the instantaneous phase of the signal based on the message. At the end of the day, you will get a signal with varying frequencies. Not like AM, where you have the same frequency. There is no changes in the frequency. So this is the key difference between AM and angle modulation in general. AM changes the amplitude and the frequency remains constant and the phase, while in angle modulation, amplitude almost remains constant while the frequency of the signal changes rapidly based on the incoming information, based on the message. So this is basically what we are. So we have explained the basic relationship between theta and omega I. Now let's go to the mathematical modeling of phase modulation, practical phase modulation and the frequency modulation. How do we do that mathematically? In phase modulation, phase is varied linearly with m of t. You define phase theta of t. To perform phase modulation, you define the following. You define theta of t to be omega ct. Yes, this is the angle in general. Yes, the angle. What's the angle is equal omega ct plus theta. Yeah, plus theta naught. Now instead of theta naught, you put the message signal. Why? Because you need to change the phase based on the message. So the message is based on the changes on the message, this plus this value changes. And as if it is embedding the information of the message in the changes of the phase. So now this is theta of t, the angle. Now what's the resulting modulated signal then? It's cosine. But whatever the amplitude, I'm not talking about a cosine omega ct plus kb m of t. Yes, m of t is basically your message. So you put it in the phase of the carrier. In AM, do you remember in AM where we put m of t? We put it basically in the amplitude. It was m of t multiplied by cosine omega ct. Yes? Anybody remembers this basic modulation? This is a double sideband suppressed carrier. You just, instead of the amplitude here, you put m of t. Here, instead of the phase of the carrier, we put the message signal. Is that clear? That's why we call this phase modulation. The previous one, we call it amplitude modulation. Now, for phase modulation, you made these changes and you end up having a modulated signal of this form. Yes? Now, I want to ask you, what's the instantaneous frequency in this case? You tell me it's super easy. Instantaneous frequency is the derivative of the angle with respect to time. Where is my angle? This is it. Derive it with respect to time. Derive the first term, omega ct, with respect to t, just omega c you get. Derive this kb m of t, you just, kb is constant, you take it out and derive m of t. This is the derivative, m dot of t. This is done, kind of a denotion, kind of derivative. Sometimes we denote the derivative by m prime, and sometimes by m dot, or sometimes by this d delta t. So all of them the same. Here we use the dot notation. Now, if m of t varies rapidly, then the frequency deviation are larger. The more the signal varies, the more changes in the phase you will end up getting, and this will affect the instantaneous frequency of the signal. Now this is, remember with me, this is for phase modulation, the first type of angle modulation. Now what about frequency modulation? Frequency modulation, frequency deviation is linear in m of t. So basically omega I of t in frequency modulation is equal to omega c plus kth m of t. The frequency deviation is linear with m of t. Here the frequency deviation is linear with the derivative of the message signal. That's the key difference. That's why we can see they are almost very similar to each other. The only difference that one varies with the message signal directly and the other varies with the derivative of the signal. In general, in this case, the angle is theta of t, the integration from minus infinity to t. Put this into the integration, you get omega ct, kf, and the integration of the message. If you want to find theta of t for the frequency modulation scheme. So these equations, just remember, let me highlight them for you. This equation and this equation. This, you have to remember them and understand the relationship between them. If you are given this equation, you directly know that this is frequency modulation because m of t is changing, or the frequency is changing directly with m of t. But here the frequency is changing with the derivative. So this is phase modulation, this is frequency modulation. Also, if I give you this equation and tell you that theta is changing directly with m of t, then this is phase modulation. But if theta is changing with the integration of m of t, then this is frequency modulation, because this whole equation is another version of this. Just when you take the integration, when you take the integration of omega I, you get theta. When you get the integration of omega I, you get theta. When you get the derivative of theta, you get omega I. This slide is so important to be understood and digested, and understand the relationship between these equations, and especially how to move from phase to frequency in both phase modulation and the frequency modulation. I hope it's clear and understandable and not difficult to follow. So now let's move on. Some of the slides are not appearing here. So now what's next? What we are, if I ask you now to draw these using block diagram or these. So basically, what do? You just take, if I ask you for phase modulation. Yes, this is phase modulation. What do? You have your message signal. Yes. And then derive it. This is the derivative. And then make the frequency changes based on the derivative of the message signal. We call this block diagram as frequency modulation. Where here, if you take the message signal, integrate it, yes, and then change the frequency based on the integration of the message, then you have phase modulation. Now, this is the basic concept of frequency modulation and phase modulation and the relationship between them. It's like this, no more, no less. The most important 4 equations are presented here, and this is the relationship between the frequency for the phase modulation and the frequency for the frequency modulation. The only difference you need to look at is whether the signal, the message signal, is derived or not. And based on that, you can determine your modulation scheme and the parameters associated with that. But let me give you, for example, some example of what kind of questions you might see in the exam or in the test. Yes. So let's see, these are all white, and let's give you one example. You are given the following signal. Yes. And this is the signal, M of t. And I tell you, modulate this using phase modulation. Using phase modulation, what do you need to do? If I ask you to modulate this using phase modulation, this is signal in general. I can give you any shape, any signal characteristic, any sinusoidal signal, triangular, rectangular, sync, whatever. And I ask you to modulate this according to phase modulation. What do? Since I'm asking phase modulation, and you know that with a phase or frequency, at the end of the day, the frequency of the carrier will change rapidly based on the information message. Yes? Yes. But I know in phase modulation, the instantaneous frequency changes with the derivative of the message, not with the message directly. True or no? True. Then can I start mapping the message amplitude or the message information directly to frequency? No, I need to derive it first. Then you first find M prime of t. Can you find this for me? Yes, it's this. Yes? You derived it. When the edge is going up, you put a constant value on the positive side. When it's going down, negative. Because what's the derivative of let's say 5t? This is kind of 5t. 5. What's the derivative of minus 5t? Minus 5. And you continue like this. Is this easy? Now, you know that the omega I changes with the frequency. Yes? When the message signal amplitude is large, means the frequency changes are faster. So basically here, this is your modulated signal, the frequency of. Then here you have this, then here you have something like this, then here, then here. You understand me? How do you do that? So this is your modulated signal. I can ask you, what's the maximum frequency? What's the maximum frequency that this signal can carry? And what's the minimum frequency? You determine this here. If from the parameters that I give you in the original message and the derivative message, you can return back to the equation that I gave you at the beginning of the lecture and find what's if I max and if I min. Now let's repeat the equation. Let's ask you another question. Ask you, I gave you m of t and told you this is phase modulation, yes, and phase modulation. And I told you modulated using frequency modulation directly. So in frequency modulation, from the equation, I know that omega. I don't want you to get confused here. Let's go to the other. Here again, you have this message signal, and this is m of t, and now we are asking for a frequency modulation, and basically I want you to modulate this using frequency modulation. You tell me the relationship between frequency and the message signal is something like this. Omega I is equal to omega C plus kf, yes, kf m of t. Isn't it this the equation? Yes. In frequency modulation, this is the equation. So basically, omega c will be given to you, kf will be given to you, and m of t also. M of t is this. You all need to determine omega I. You tell me this is super easy. I just need to change the frequency based on the message signal. So basically, as the amplitude here increases, the frequency increases little by little. So here you have some increase in the frequency, means it becomes, and as the frequency goes, as the signal goes down, the frequency start to decrease. So decrease means the repetition reduces, or the cycle becomes larger a little bit, and you continue like this. So this is the key. And if I tell you find the maximum frequency that this signal can have, you tell me, I know omega c, I know kf, I know the maximum amplitude that this signal can reach, let's say 1 plus 1. You put just plus 1 here, you take wi, and if it is and if I ask you about the minimal frequency that this signal can have, you just you find the value here, let's say -1, and you substituted this here, you multiply it by kf, add it to wc, you find omega I, and you can draw the shape, which is pretty super easy to find. Now you transmitted the signal and the receiver captures it. How the receiver can decode the signal back? The receiver uses filter to tune to certain frequencies and map these changes in the frequency to amplitude changes. So the signal is, he has kind of a reference, and the frequency starts with this value, and starting from that value, and based on the value of the frequency, the receiver changes the amplitude of the signal. So as you can see here, the frequency is increasing little by little, so the receiver knows that the signal is going up little by little with certain slope. These information are shared ahead of the time, and then goes down, goes up, and then he can detect the signal back. Kind of. It won't be exactly perfect, but close to what you transmitted. So basically, these are the key important concepts, key important formulas, and equations that you need to be aware of so that you can answer or solve any question related to frequency modulation and phase modulation. So with this, we conclude our lecture and stop here for now, and we continue after a while with the second part related to frequency modulation. Thank you very much for your attention, and meet you in the next lecture.